Hello, everyone. Good afternoon. My name is Norb. You see me signing here on screen. I am a deaf man. I use sign language to interpret. So you're going to be hearing a female sign language interpreter's voice as I sign. We will start with a short story to illustrate the importance of surface analysis in our everyday life before diving into the details. The US Constitution says all people are created equal, but are children building toys? A frugal parent was looking for an opportunity to buy a cheaper building toy for their child. So they brought brand C blocks, C for cheap. The kid was having fun, all seemed well and good. Then several of the cheap blocks started to fracture. What could be causing the blocks to break if the data is not showing much? Analytical sleuths at our company, Physical Electronics, had an idea. We build tools to look at the surface of materials rather than the bulk. What if we put the building blocks in one of our machines? We used a technique called X-ray photoelectron spectroscopy, which irradiates the surface of sample with X-rays and collects the generated electrons from it to provide chemical information. It turned out that the two brands are indeed different. The cheap blocks had a higher content of silicon in the form of silicates, which was attributed to the heavy use of fillers, perhaps to save money. The cheaper building blocks also had a trace amount of lead not seen in brand A blocks. Not only the cheaper brand of blocks broke easily, but the children are also exposed to lead. Perhaps being nearly cheaper than free food samples at Costco isn't always a great idea. I am starting the talk with a brief discussion on what surface analysis is and why surface chemistry is important, along with the diagram showing the extent of surface effects in terms of the number of atomic layers below the sample surface. Corrosion, or rust, happens at the surface. Adhesion of a material to another takes place at the surface and occurs or doesn't due to some failure. In catalytic converters, the gaseous phase interacts with the solid surface to transform harmful gases into safe materials like water. Medical devices form a contact with the human body. The surface interaction between rubber and asphalt keeps our cars from sliding off the road. Surface effects play an important role in thin films like paint, windows, and computer chips. Consequently, there is a significant interest in surface chemistry and means to analyze surfaces in order to develop new products and improve existing ones. This is where surface analysis comes in. When we discuss surface analysis today, we mean specific ultra-high vacuum techniques that will be introduced in the next slide. Physical electronics, sometimes referred to as PHI, manufactures such ultra-high vacuum surface analyst instruments to provide detailed surface and thin film characterization. Our three main instruments are XPS, Auger, and TOF-SIMS. They all provide our customers with tools to solve challenging materials problems and as well as the development of new processes and products. PHI also offers contract analytical services to customers on a sample basis, providing access to state-of-the-art capabilities without needing to purchase the full instrument. This is a famous diagram comparing various analytical techniques by their resolution and detection limit that you may have seen. I have circled in black the surface analysis techniques in comparison with other more common techniques such as SEM EDS. SEM-EDS is a technique that uses electrons to form images and for elemental analysis exceeding optical microscopy's spatial resolution. Surface analysis techniques are uniquely positioned for information inaccessible by other imaging and bulk techniques. For example, SIMS is the only analytical technique that can detect species at a parts per million to billion with a spatial resolution in the nanometer range. Interestingly, the three surface analysis techniques form a triangle on this chart. Perhaps they are the Bermuda Triangle of analytical techniques, where strange things happen and mysteries are solved. Surface analysis techniques use different probing beams to analyze the sample surface, resulting in different signals emitted from the sample surface. They have their respective strengths, as shown by the blue text in terms of resolution, detection limit, and the type of information collected. They also have a larger role in specific applications than others, as will be shown shortly. The diagram on the left summarizes some of the most important differences between the surface analysis techniques in terms of information depth and the size of the analysis area. We will come back to this diagram and table for us to fully connect the dots later. I'll start with some background and some motivation for the Auger electron spectroscopy, or AES. Scanning electron microscopy, or SEM, is a surface analysis technique capable of imaging the surface with a spatial resolution on the order of nanometers, something not possible with optical microscopy. While it is not part of today's webinar, as it is an imaging technique rather than a chemical analysis tool, we include a comparison of a popular elemental analysis attachment for SEM called energy dispersive X-ray spectroscopy, or EDS. EDS utilizes a high-energy electron beam striking the sample surface to generate X-rays for detection. SEM-EDS is a popular entry-level option for many laboratories for high-resolution microscopy and elemental analysis. Its capabilities are more well-known compared to the surface analysis techniques discussed in this webinar. In this sense, SEM-EDS is a gateway to the broader world of surface analysis because of its relationship with Auger. SEM-EDS sits somewhere between being a surface-sensitive analytical technique and a bulk technique because of its larger sampling depth of approximately 300 nanometers versus the nanometers offered by Auger, XPS, and TOF-SIMS. The surface analysis technique most comparable to SEM-EDS is Auger. The table here shows the strength of Auger versus EDS, which is its high spatial resolution on the order of 10 nanometers, compared to more than 300 nanometers for SEM-EDS. Auger is an excellent candidate for the imaging and chemical analysis of nanoscale features on the surface. The SEM image in the center of the slide was taken on an iron sample where manganese sulfide was intentionally included. Manganese sulfide is sometimes added to steel to improve its machinability. However, it can lead to corrosion pits in the surface, like the dark spot shown in the center of the SEM image, potentially leading to larger material problems down the road. Corrosion costs the global economy about $2 trillion annually. To understand the role of high-resolution elemental imaging in Auger in solving such an important problem, we start with the events that occur when the electron beam scans the sample's surface. In the diagram on the left, we see three events: secondary electrons, Auger electrons, and characteristic X-rays. Characteristic X-rays are also generated in the process, which are measured by EDS. The challenge with conventional EDS is that the volume below the surface excited by an electron beam is similar to the size of the pit on the surface by looking at the scale bars in the diagram on the left and the SEM image on the center. This means that the individual elements, while detected, would not be spatially resolved, limiting our ability to characterize an important problem in order to mitigate its economic impact. Auger offers the best of both worlds, with SEM-like imaging and EDS-like elemental analysis. The elemental map on the right was generated with Auger electrons emitting from several nanometers below the surface. The result is a high-resolution image showing the distribution and segregation of various species making up the pit. Auger's strength in elemental analysis can be complemented with the ability to probe chemical bonds using another surface analysis technique, X-ray photoelectron spectroscopy, or XPS. XPS has a similar sampling depth as Auger and measures electrons from the sample surface using an X-ray beam. HAXPS, a mode of XPS in PHI instruments, uses X-rays with higher energy than conventional XPS for a larger sampling depth, up to 30 nanometers compared to 10 nanometers for XPS. XPS brings non-destructive depth profiling not possible with Auger or TOF-SIMS. XPS and HAXPS are the best surface analysis tools to study chemical bonds due to nearest atomic neighbor interactions in the surface. Both XPS and HAXPS also offer imaging capabilities, albeit at a larger spatial resolution compared to Auger. XPS's imaging ability come in the form of generating images using secondary electrons that are created when X-rays strike the sample, as shown with this heart stent example. XPS imaging with PHI instruments is called scanning X-ray imaging, or SXI. Scanning aspect refers to the instrument's ability to raster the X-ray beam to produce the images. The SXI image on the left shows contrast between dark and light areas on the stent surface due to the compositional inhomogeneity. In this case, the customer was characterizing the stent surface in order to understand chemical states at the surface. For example, the type of oxide present at the surface. While navigating around the surface to select analysis locations, they noticed a dark spot on the stent surface. XPS spectra were collected on and off these dark regions to capture a range of binding energies at a low resolution in the survey spectra. Survey refers to a rapid general scan to determine all elements present on the surface. Binding energy is the energy required to eject an electron from the atom and is characteristic of both the element and its chemical state. We know which elements are present from the survey scan and can then zero them in for a high-resolution scan as shown by the carbon spectrum on the right. The carbon spectrum of the dark region revealed multiple peaks representing different carbon chemical states: carbon bonded to carbon, oxygen, and fluorine. These chemical shifts are key to XPS, indicating changes in binding energy due to different chemical bonds. Colorized curves under the carbon spectrum help identify various chemical states. The dark spot in the image was identified as oxidized fluorocarbon contamination. This XPS imaging approach of locating a small feature can be extended to memory alloys, for example, to determine whether or not the surface is metallic or oxidized. The ability to discern between different chemistries is a strength of XPS.
So now I'm going to shift our talk to talking about Stratify. And it's a software that determines the film thickness in a non-destructive manner. We have an example of a medical device application, similar to with the stent that we saw earlier in the previous slide. This is an extension of that. And how the software works is it will collect XPS data and then load that into the PHI software, which is called, again, Stratify. The user can instruct the software this material should have 3 layers. For example, a carbon layer on top, and then a metal oxide layer below that, and then a metal substrate. And then the software will then in turn do the calculations to determine the film thickness of each of those layers in the output. I will show you how that works on our next slide. We have another example of a medical device using XPS, and this time it's an investigation that's more focused on the R&D side of the house rather than failure analysis. A customer may be interested in measuring the thickness, the individual film thicknesses, the coating on top of the metal device structure in order to qualify a change in the process conditions. Again, that would be a manufacturing environment. This micron-sized wire structure, as you can see here, is shown in the SXI image on the left, with the orange line representing the acquisition area. So bringing a medical device into the human body is not trivial, certainly is not trivial. And that's because you need to open the skin, find the affected area, find the correct location, and then implant the device. This will certainly affect in a negative way the environment, could induce a lot of complications as the body learns to respond to the foreign object that is now located within it. So that coating on the implanted device certainly can assist minimize and manage those complications. So because of the limited area of the analysis, with such a small sample geometry, we have a few analysis techniques, including ellipsometry, as well as a cross-section using an electron microscopy. So the challenge included the sample destruction, right, during the analysis, as well as complicated data analysis after the acquisition. So we at PHI have intentionally simplified the data analysis process using Stratify. So that coating thickness could be assumed right away with XPS and the use of Stratify. First, the XPS spectra collected shows a large carbon signal, which represents an organic material in the coating. We also have a titanium spectra, which represents the oxygen surface. There's titanium oxide at the surface. And then the substrate is the alloyed nickel titanium. And here you can see in the spectra of nickel, where you see that metal, that nickel signal. So knowledge of the sample composition and the chemical composition is entered into the software, Stratify. And the analysis, we're telling this system that there's 3 separate layers: a carbon layer, a titanium oxide on top of the substrate, and then the substrate itself. Stratify will then automatically do the calculated thicknesses of each of those individual layers, and then show a plot, as you can see here. It's an actual plot from the software itself, showing the thickness here with approximately 6 nanometers for the organic layer at the top, with about 0.4 nanometers for the titanium oxide at the surface, and then with the nickel titanium substrate. So this thin film, this non-destructive thin film, is measured by XPS and can be applied to various conductive and non-conductive materials in a variety of industries, right? Including semiconductors, batteries, things of that nature, right? So XPS will enhance the information of the depth profile of the sampling depth. And that is a tool called HAXPS, Hard X-ray Photoelectron Spectroscopy. We use hardened X-rays with a higher energy level compared to the softer X-rays, which are used in conventional XPS. So to show what HAXPS can do with its larger sampling depth versus XPS, we have a multi-layered film of yttrium oxide on metallic chromium, metallic chromium layer, and titanium layers. We would like to analyze this with XPS because previous analyses using transmission electron microscope or microscopy with elemental analysis suggests that there is an oxidized layer at the buried interface between the amorphous yttrium oxide and the chromium layers. Because of the thickness of that topmost layer, we cannot detect the interface using conventional XPS. We're using HAXPS in order to do that. So HAXPS gives you a greater sampling depth. And with HAXPS, we see all the way to the titanium layer. To look at the sample with XPS, there appears to be only one oxidation state for yttrium, as shown by the blue curve, even though we have 2 separate peaks here. These 2 peaks are known as doublets, and that's due to a process called spin-orbit splitting as a result of the interaction between the photoelectron spin and the angular momentum. The doublet notation is represented by the subscript, which is next to the orbital letter. And HAXPS is also showing a single yttrium peak in the red curve. Now, on the other hand, there appears to be several peaks for each of those doublets in the HAXPS, right? We were seeing here a spectrum of chromium, and we also see the strength of HAXPS with its ability to detect the buried chromium and titanium layers that conventional XPS cannot. As a side note, for this sample, The reason for not being able to detect the silicon substrate is because of the generated photoelectron's ability to escape from a deeper layer depends on the material's composition. In addition to selecting XPS or HAXPS to modify the sampling depth, we can also actually tilt the sample with respect to the detector inside the instrument. Tilting modifies the sampling depth by modifying the distance that a photoelectron generated below the sample surface must travel to escape to be detected. Right? TOA is the takeoff angle, which represents the tilt of the sample. A TOA of 90 degrees means that the sample surface is normal to the axis of the detector, meaning facing it head on, providing the greatest sampling depth. Conversely, a takeoff angle of 30 degrees tilts the sample surface away from the detector, resulting in a grazing analysis of the surface. And this reduces the sampling depth. So with a grazing angle of 30 degrees, information on the shallowest layers under the surface is enhanced. There is a higher relative ratio of the chromium 5+ and the 6+ states to the metal compared to the takeoff angle of 90 degrees. So this suggests that the higher oxides are enhanced near the top of the chromium layer. So in this case, it was useful that the analysis could be performed without needing to sputter the sample using an ion beam to reach the buried interface. Ion beams often alter the chemistry of the matrix, leading to the loss of valuable information, such as the two oxidation states shown here. So far, we've seen how Auger, XPS, and HAXPS give us information about the elements and short-range chemical bonds present at the surface. However, these techniques do not have the ability to investigate the molecular structure of a material beyond the nearest atomic neighbors. Now, normally this would not be a problem for relatively simple materials like metals, where the nearest atomic neighbors are the same everywhere in the material. It becomes challenging when related to large molecules. So, for example, the carbon-carbon and carbon-oxygen bonds are extremely abundant in organic molecules. They may show up in XPS spectra of carbon as two peaks. However, they could represent many different organic molecules. So this is where time of flight secondary ion mass spectrometry, also known as TOF-SIMS, comes in. So TOF-SIMS is a surface mass spectrometry technique, which is key for analyzing molecules on the surface with a spatial resolution in the nanometer range. So in TOF-SIMS, a probing beam of ions called primary ions, they're going to fragment and eject molecules from the surface. So that time of flight moniker refers to the measurement of time that it requires for the ejected secondary ions to travel from the sample surface to the detector. So we separate and identify the molecules based on their mass, and mass is related to the flight time. So the larger molecules require more time to reach the detector versus the smaller molecules. The liberated molecules often come from only a few monolayers below the surface, making them extremely surface sensitive. So TOF-SIMS collects both surface-sensitive data on elements and molecules within the first several monolayers, as well as imaging their lateral distribution via secondary ion images. The distinguishing thing with TOF-SIMS is that we can image large molecules, unlike Auger and XPS. This application of molecules is critical to industries where polymers play a large role, such as paint, filtration, and adhesives. So each pixel here represents a full mass spectrum. We typically have a total ion image representing all detected ions from the sample. TOF-SIMS really is a powerful technique where the scientists can reprocess the data to gain different insights. So, for example, we can look at a certain peak in the mass spectrum representing molecule A and plot a chemical map representing that molecule. The scientist could also want to understand how molecule A relates to molecule B. They can then retrospectively process the mass spectrum to image molecule B. This is a TOF-SIMS example of a thin film on a polycarbonate substrate. The depth profile on the left highlights TOF-SIMS' ability to track large molecules in the depth of organic materials not possible with either Auger or XPS. The depth profile only shows the integrated intensities of detected ions in both the X and Y directions as a function of depth in TOF-SIMS. Viewing the same data in 3 dimensions enables the analyst to collect information on the homogeneity of the surface. For example, the distribution of uracemide shown by the red color in the top row. Urucimide, pardon the interpreter error. So urucimide is a slip agent used in the manufacturing process to reduce friction of plastics as they move through different processes. Because urucimide can mask useful information on the underlying thin film that had been deposited on that polycarbonate substrate, we can use an ion beam to lightly sputter clean the surface to remove the urucimide layer. The result is accessible information on the thin film itself that is distinct from the polycarbonate substrate, shown by the blue and yellow colors in the bottom row. A careful scientist looking at the slide might say, hey, this begs the question of how we know the mass-to-charge ratio of 211 represents urucimide. It could represent one of many possible kinds of molecules. So this is another example of a scientist being faced with many possibilities that could explain a peak in the TOF-SIMS mass spectrum. While reconstructing a TOF-SIMS depth profile and a 3D profile from the mass spectrum at top left, as shown in the images at top left, top middle, and top right, the scientist notices that there are polypropylene materials coated with an unknown material in green, represented by the mass-to-charge ratio of 284. In the TOF-SIMS data analysis software, you'd see a list of many possible chemical formulas. Okay, moving on. To confirm the identity of a large ion fragment in TOF-SIMS, we use tandem mass spectrometry, which is a broad technique that analyzes chemical samples by using more than one mass spectrometer. It is used to break down molecules and analyze their molecular structure, and is an important surface analysis tool. Secondary ions emitted from the sample surface travel in a circular path toward the detector called MS1. In this circular path, the ions are deflected by 3 pairs of focusing electrostatic plates. This circular motion makes it useful for the analysis of samples with rough surfaces. Now recall that TOF-SIMS is a technique that measures the time it takes for an ion to travel toward that detector based on the distance from that sample surface. So a rough surface means that the distance to the detector is not uniform and leads to a loss in mass resolution. The triple focusing in PHI TOF-SIMS instruments eliminates the challenge inherent in these rough surfaces. So with an unknown peak in the mass spectrum representing some large molecule, we can perform mass spectrometry again on that very molecule. And this is done by adding a separate time of flight column with a second detector, which is called MS2, as well as a precursor deflection mechanism to select and redirect an ion with a known mass, but an unknown identity into that second column, right? A chamber of gas in front of that second column further fragments the selected ions. This is shown by the red ion with a mass to charge ratio of about 600 in the animation. So what we do is we select the red ions from the main mass spectrum, MS1, and send them into the second spectrometer to collect a second mass spectrum. This method excludes all the other ion species in the original spectrum, reducing the number of possibilities for the unknown. So we go back to our problem of the ion species with the mass to charge ratio of 284. So we can select this peak in the main mass spectrum MS1, and then further fragment the respective ions to produce the tandem mass spectrum, where the largest mass is equal to the mass of the ion selected in the first mass spectrum. So the signature fingerprint of the resulting tandem mass can then be compared to the various databases of mass spectra. So in this particular example, a match is found in a NIST tandem mass spectrometry database, which is steramide. So tandem mass spectrometry in PHI TOF-SIMS confirms the 100% the identity of the peak with a mass to charge ratio of 284. And that's out of the many possibilities with a similar mass. So steramide is a common waxy polymer which is used as a release agent on plastic bags. So a lubricant or a corrosion inhibitor. They're even found in cosmetics as well as shampoos. So TOF-SIMS data interpretation and peak identification without compromising space resolution and speed. Confidence in TOF-SIMS peak identification goes from I think to I know. So just wanted to summarize the 3 main techniques that are used within ultra-high vacuum, Auger, TOF-SIMS, and XPS. They each have their own strengths. Auger is best used for spatial resolution, analysis of nanoscale features, as well as elemental analyses. TOF-SIMS, on the other hand, is best for molecular analysis at the surface with nanoscale spatial resolution. But that you really can't find anywhere else. And then lastly, we have XPS, which is a good use for analysis of chemical states at the surface. For example, I'll tell you the difference between metal to metal bonds versus metal to oxygen bonds in the form of a metal oxide. Thank you so much for listening to today's presentation.